Hello everyone, welcome back to the second session in the context of removal of nitrogen and phosphorus. In the first session or the previous session, we looked at understanding nitrification and then denitrification, right? As in first you are going to change the form of nitrogen from ammonia, which is reduced form of nitrogen, to oxidized form, right? NH4 plus going to or ending up as NO3 minus. But again NO3 minus is soluble. So, you are going to use or promote different kinds of bacteria by changing the conditions, and these conditions are such that it has to be anoxic, right. Let us look at this. So, we have nitrification, we looked at this. So, two steps, first ammonia oxidation to NO2 minus, so thus ammonia oxidizing bacteria, and NO2 minus going to NO3 minus, nitrite oxidizing bacteria. Overall, it will look like this obviously, as in NH4 plus going to NO3 minus, but please understand that there are series of steps. And these are autotrophic, as you see, for their cell mass they do not use a source, organic source of carbon, right. They do not use an organic source, they use an inorganic source of carbon. So, thus autotrophics or autotrophs, let us say. And one aspect to keep in mind is that they grow slowly. So, what does that mean? Meaning that you have to have high cell residence times, let us say, right. So, that is one aspect, and also their yield is less, right, less, what do we say, number of microorganisms or new cells produced per what do we say, mass of or unit mass of the substrate or food that they are consuming. I think we will come to this later, so let me not digress here. So, denitrification, okay, conversion of what do we say, TK into nitrate, we already summarized this in the previous slide. So, let us move on, two steps, and overall nitrification reaction, yes. And here one aspect to note is that if we look at it from mass point of view, 1 gram of nitrogen uses 4.5 grams of oxygen. So, that is a considerable requirement. So, whenever we are looking at removal of nitrogen, the need for oxygen, right, goes up a lot, let us see. Why is that? Because then your costs also increase, right. But it is not as if it is 1:4.7. Why is that? Because some of the nitrogen will also be, what do we say, fixed in the cell mass, let us see, right. I think we might have the equation somewhere here, okay. So, we will come back to that particular equation, okay. So, we have it here, it is NH4 plus 1.86 O2, and then here you see it is NH4 plus 2 O2, right. So, you understand that some of that is going to go into new cell mass, and CO2 is being used for production of the new cells. Again, this is the overall reaction where NH4 plus is being degraded to nitrate, and also the new cells are being produced, right, new cells. So, that is one reason why we talked about this, though theoretically it might seem like 1 gram of nitrogen consumes 4.7 grams of nitrogen, actual requirement might be slightly less, okay. And as thus, I guess, if when you say you are going to consume carbon dioxide, right, it is not carbon dioxide, or you have to, I guess, produce carbon dioxide too. So, HCO3 minus will be consumed in this process, right, this carbon dioxide will be released. So, why is that necessary? Because it will lead to decrease in the alkalinity, which will give me an idea about the acid neutralizing capacity of water. So, these waters now you can either the pH will be affected, or whenever you add an acid they can't stop the decrease in pH, but we are not going to digress there. But that is one aspect to keep in mind, because you see that during what do we say, nitrification process, alkalinity will be consumed, let us see. Again, the overall reaction turns out to be something like this, right. You have both the nitrification to NO3 minus and new cells. Let us move on. So, characteristics of nitrifiers. Nitrification is thermodynamically less favorable than oxidation with oxygen. For example, if you have, what do we say, if you look at the energy and such, and I think we looked at this, okay, let me explain it in a better manner. We looked at the COD test, I think here we had time, and here we had the COD or such, let us see. and I think we saw some graph like this. And then we see that when there is no more carbonaceous, what do we say, oxygen demand, then you have the nitrogenous oxygen demand coming up. Why is this? Why is it that bacteria don't use nitrogen when there is carbon present, let's say, or organic carbon present? Because in those conditions, a different kind of bacteria which gain more energy from the degradation of organic carbon in the presence of oxygen, right? That gives out more energy, and those microbes thrive. So that's the reason why typically they grow later. That's one of the reasons, and that's what we are trying to say. Nitrification is also less thermodynamically favorable than oxidation with oxygen. I guess it's not greatly written or poorly framed sentence here, but you understand the issue. And they are sensitive to DO. So the DO is typically relatively higher, right? This is one way to control denitrification or nitrification by maintaining a lower DO. So if you don't want to have nitrification and thus later denitrification, what is one way? So you can maintain relatively low DO without being too close to 0, and at this relatively low levels you can still have aeration occurring, but nitrification will not occur. And another aspect is toxins. I believe we discussed this, so I will skip through this. Toxins, they affect the ammonia oxidizing bacteria or nitrite oxidizing bacteria greatly than they can affect the other heterotrophs or the heterotrophs out there. So that's one aspect. They are highly sensitive to toxics, and as we mentioned earlier, slower growth. So they require a higher retention time than the heterotrophs, let's say, right. So longer retention time is thus required to achieve nitrification in an activated sludge tank, let's say, and time required increases obviously in lower temperatures because the kinetics is the case. So obviously you need to look at theta C, let's say, right. So that's something to keep in mind, theta and theta C. So denitrification. So in the second stage of nitrogen removal, heterotrophic bacteria. Why heterotrophs? Because they need a source of organic carbon. But unlike earlier, what's the electron acceptor here? It's not oxygen, but it's NO3 minus, right, that was produced from nitrification. So electron acceptor is not oxygen, so it's not aerobic process, but it's an anoxic process. Yes, so that's what you have, and that leads to formation of N2, right. So under anoxic conditions. So this is what you have, NO3 minus NO2 minus reduction, and finally you end up with N2, right. Again, denitrifiers. So that's something to keep in mind. Obviously, if there is oxygen, you will see that I think we have the relevant table that I want here. Okay. So this is the case that we will compare glucose, the amount of energy released, and for denitrification, the amount of energy released, let's say. So obviously, as you see, not a great lot of energy, but some energy or relatively more energy is released when we have oxidation of the organics by oxygen. So obviously, you should not have oxygen, because if oxygen is present, the kind of microbes that thrive will be different, and you will not have this reaction taking place. If you don't have this reaction, obviously NO3 minus to NO2 will not happen. So thus you have to prevent oxygen from being present. So that's something I wanted to mention. So if organic matter is present, fine, that will be used, right. Organic matter can be the wastewater itself, right, or the waste in the wastewater itself, that can be used, yes. But depending on how you are configuring the system, if you don't have organic carbon, where is the electron donor? There is no electron donor. So in that case, you add carbon or source of organic carbon. So methanol or acetate is added sometimes, let's see. And I guess here is the relevant redox reaction, let's see. CH3OH and CH3COOH, right. Carbon is being oxidized, right, and nitrate is being reduced, right. So electron transfer. So that's something that you can see. Again, when are you going to add methanol? When you don't have enough carbon for driving this particular reaction. And we already looked at this, so I will skip this aspect. So let's just look at one system. So in a conventional ASP, let's understand nitrogen removal, assuming that the theta C and theta are such that, are long enough such that you have nitrification taking place. We know that they are slow growers, so they need more time. So let's say theta C is more, let's see. So, NH4 plus and BOD are coming into the effluent here, right. And here assuming that we spend or let the bacteria spend enough time such that nitrifiers are also what do we say in the picture, you are going to have some nitrification and then BOD removal. So, that is what you see, soluble carbonaceous oxygen demand, it is decreasing, right, that is something that you would expect. So, NH4 plus is also decreasing assuming that we maintain the conditions, and NO3 minus is increasing. And then what is happening though, we will end up what do we say discharging NO3 minus into the effluent, but we know that NO3 minus is not something we want to or should discharge into the wastewater. Again, there are standards, primary reason being NO3 minus is toxic to us too, right, to humans. So, how do we change it, right? So, here the key is to understand that this NO3 minus is formed when you have oxygen, and NO3 minus is removed to nitrogen when you have no oxygen, right. So, that is the key. So, you will have anoxic conditions and aerobic conditions. So, how do you do that? Let us see. So, nitrogen removal, let us look at one other aspect here. So, here you have aeration. So, during this process let us understand how the system is going, the same case as earlier, the first part is the same case as earlier. During aeration BOD removal takes place. So, that is what you see, this BOD is being removed, the BOD or COD, soluble COD is being removed, right. So, that is happening during aeration, and assuming that we maintain the theta C such that nitrification also takes place, you are going to see formation of NO3 minus, right. So, NO3 minus is formed. So, here after aeration there are two cases. If there is not enough organic matter, because I now have NO3 minus, I want that to go to N2, but I do not have an electron donor. So, I need to have some organic compound, right. So, that this is what can maybe take place. So, if the organic compound is not already present in the water, I have to add it. So, as mentioned we are going to add methanol, let us say. So, that is what you see. So, that is why while the organic COD or COD is decreasing until now, after addition of methanol you see that it increases, and then the methanol is being degraded by this particular reaction, and simultaneously NO3 minus is being reduced to N2, right. So, let us say this is the path, okay. So, this is the path for NO3 minus, but if I do not add methanol, right, what is going to happen? There will still be some BOD or COD in this treated wastewater. So, that can act as the source of my organic carbon for this reaction, but typically in my treated wastewater the organic carbon will be relatively less, right, and thus obviously you know this rate of this reaction will be relatively slow, and if there is no methanol or additional organic carbon present, so you are going to have a slower removal of nitrate, or even a more or less slower and finally lower removal of nitrate, let us see, right. So, that is what you see here in this anoxic tank, obviously nitrogen is the end product, that is what you see. So, typically what is it that we have? Some additional information, COD to TKN, if it is greater than 12 then it can lead to, or you can sustain the system to lead to denitrification. So, that is one aspect to keep in mind, right. But in general for wastewaters without adding a carbon source, you know, looks like you can't achieve that level of denitrification or complete denitrification, right. So, that is something to keep in mind. So, I guess Workman process, yes. Let us move on, nitrogen removal. So, what else do we have? Different kinds of what do we say configurations. So, Lutzak-Ettinger process. So, what do we have? Here please note that the anoxic tank is present before the aeration tank, but then you know how is it that I am going to what do we say have nitrate here. For example, in the anoxic tank you know that NO3 minus goes to N2, but it needs some organic carbon. Fine organic carbon is coming from my influent wastewater organic carbon, my waste is the organic carbon, right. I want this reaction to take place, fine, but where is the nitrate coming from? So, that is why you see that this nitrate will be recycled from here, if not from here it will be recycled from here, let us see, okay, or probably okay even here, that is also fine, right, because you do not want it to leave a lot from here. So, depending on that you can recycle from here or here. So, you are going to recycle this. So, here what is going to happen, you have recycle, that is bringing in nitrate from the treated wastewater. So, you have nitrate here, you have the organic compound here, right, and then this anoxic process goes forward, or denitrification goes forward, and N2 is degraded. So, what is it that we see? Wastewater is the carbon source, as I mentioned, and because there is considerable what do we say, carbon or organic carbon, because wastewater is influent wastewater has higher carbon. So, potential is faster, or the kinetics will be faster with respect to the denitrification rate, right. But inefficient carbon, what do we say? Okay, I understand what I should have done, a minor aspect. So, let us consider this case, okay, the case where we are only looking at what do we say, nitrate coming in from this particular aspect, let us say, or here, okay, and note that some nitrate will leave the system from here. So, what is happening though? So, looks like there might not be what do we say, enough nitrate here. So, that is one aspect to consider. So, the removal is based on nitrate limited, let us say, right, inefficient carbon utilization. So, again in the aeration tank, obviously the soluble COD is decreasing, and in the aeration tank now you have oxygen, and the organic ammonia and NH4 plus is being degraded to NO3 minus, and from here again this NO3 minus is being recycled to come back out here. So, you have the removal of, or pre-anox, I guess, right. So, that is something to keep in mind, right. Let us move on. So, another adaptation based on what I just mentioned earlier. So, we are internally recycling it, right. Here there are two cases or aspects that I want to mention. Earlier, if you remember, I was skipping ahead and saying that you can recycle from here, but this case let us just consider that we are recycling only the sludge which has nitrate. Two reasons to what do we say, recycle: one, to bring nitrate out here, and also to bring out the microorganisms, but nitrate is leaving the system. So, thus we have another way, as in you have what do we say, nitrate being recycled from the aeration tank, internal recycle. So, internal recycle, this ratio is what do we say, pretty important. So, what do we have now? We have higher nitrate concentration coming into the picture, because you can recycle or control this rate, and at this particular point now you have both high organic compound or concentration and also relatively high or enough nitrate concentration. So, this reaction is pretty much fast compared to the previous process, right, and you will have N2 and CO2. Obviously, you need to balance this reaction. So, let us just understand the system here, and here obviously we are recycling it for the sake of the microbes, and any nitrate present here will also come in here, right. But overall, if you look at it, the much lower nitrate concentrations will be achieved here, right. So, that is something to keep in mind compared to this process. Yes. So, let us see, here we have high what do we say, COD and high enough nitrate and efficient utilization in both contexts. So, you have what do we say, both the organic carbon decreasing and also nitrate being denitrified, right, at this case. And here at this stage again in the aeration process, your organic compounds are further decreasing, while the ammonical nitrogen and the organically bound ammonia is being oxidized to nitrate. At this point we are having the internal recycle. So, this goes back here, and we are now going to have enough nitrate there. That is why this what do we say, concentration is coming back down. Why is that? Because nitrate recycle internal, because of the nitrate recycle. You can compare that with this particular system, let us say, right. So, that is something to keep in mind. Okay, let us move on. I guess we have different such process or aspects, but we already looked at that. So, another case is when you have anoxic aerobic in series, and influent is given out into the anoxic tanks to provide for your organic compound. In anoxic tank, what do you need? You need nitrate, and that is coming in from the recycle, and you need organic compound that is coming in from the influent, again in series, let us say, right. So, again this is called step feed, and again in SBR2 sequential batch reactor, based on how you are filling it and whether you are and how you are providing air after filling it. You can have alternate anoxic and aerobic conditions, let us say. So, right, depending on how often or how frequently or with respect to time how you are providing oxygen within the same tank, you can have your anoxic and aerobic conditions, right. Let us move on. So, next aspect is removal of phosphorus. As I mentioned, phosphorus is typically the limiting nutrient, and we will move on without spending too much time there. Unlike what do we say the case of nitrogen, the phosphorus that is organically bound, it's relatively difficult to be degraded by the microbes, because it seems like this will take time to be, what do we say, become soluble, let us say, right. So, to go to PO4 3 minus or the orthophosphates, and these orthophosphates are the form which are more easily taken up by the microorganisms. So, typically orthophosphates relatively easily taken up, and we are typically also concerned, at least in India, because at least in India we are concerned about polyphosphates like sodium tripolyphosphates, right, sodium tripolyphosphate. Why is that? Because we use a lot of detergents, and I think people might have seen the case of Bangalore and such, where phosphorus was released in the case of, or in the form of, or due to excessive usage of detergents. But again, polyphosphates too difficult to be absorbed by the microbes, so thus they are a concern. So, try to avoid detergents that have a lot of phosphorus. So, total inorganic phosphorus is orthophosphates plus the polyphosphates, but in general only the orthophosphates are taken up by the relevant microbes relatively easily. So, one aspect here is that there is still considerable uncertainty to look at to identify the forms of P that are readily accepted by or assimilated by the microbes, but in general orthophosphorus. So, okay, before we go further, let us just try to understand the picture. For BOD, how are we doing it? Organic compound plus oxygen goes to CO2 plus H2O, right. Oxygen is the electron acceptor. So, for BOD, and I am decreasing my organic compound. For nitrogen removal, how am I doing it? Again, redox process. This is a redox process, right. Oxidation and reduction is occurring. This is being oxidized, this is being reduced. So, for nitrogen too, what are we doing? Initially NH4 plus, we are converting or oxidizing it to nitrates finally, and nitrates in the presence of the organic compounds, we are going to, what do we say, oxidize the organics, but this time electron acceptor is nitrate, and we are going to these products, let us see, right. So, again both are redox process based, but with respect to phosphorus that is not the case though. So, here we are trying to, what do we say, let a certain kind of microbes thrive, and the microbes that we are trying to, what do we say, propagate here are called phosphorus accumulating organisms, right, phosphorus accumulating organisms. So, obviously as the name indicates, these what do we say, microbes or the phosphorus accumulating microbes can accumulate phosphorus, but again these are specific what do we say, microbes. So, thus you need to create the conditions specific to these microbes to let them thrive, and in general these microbes thrive under what do we say, two conditions, both anaerobic and aerobic. Well, I should not say under two conditions, under the conditions which are put forth by having alternate anaerobic and aerobic, let us see. Why is that? In such conditions, the microbes are under stress. In aerobic, when they have oxygen and carbon source, they have access to energy. But under anaerobic conditions, they don't. They need to, gain or, still function and thrive. So, they will accumulate, pardon me. So, these phosphorus accumulating organisms are acclimatized to these conditions, let us say, as in when we provide alternating conditions of stress and no stress, anaerobic and aerobic. So, let us see how this works out. Again, what are we trying to do? We are trying to form these phosphorus accumulating organisms. Once we form them, and then when we settle them out in sludge, we are going to remove them. So, it is not degradation, it is just that we are trying to see to it that the phosphorus in the water is accumulated by these PAO or phosphorus accumulating organisms, and then later you are going to remove them or separate them from the water. That is the principle. But again, we need to create or provide conditions in which these PAOs thrive, and again stress and no stress, let us say. So, first let us look at aerobic conditions. What do these PAOs do under aerobic conditions? So, let us say this is the relevant cell. Okay. Under aerobic conditions you have oxygen, and you have what are called PHBs, polyhydroxybutyrates. Okay. So, what happens here? Here you have this being oxidized and going to CO2 and let us say H2O. These are source of, you can say, a carbon, a type of compound, let us say, that is stored internally, let us say. So, here these phosphorus accumulating organisms under aerobic conditions do not need, or at least for this part of the process, do not need an external organic compound, let us say, right. So, what is going to happen? Oxygen is being used and this is going to happen, and then energy is released. Here this energy is released, and there are two ways. Okay. So, let us take the simpler way, we will look at the other case later. And during this condition, the energy that is given out will be used to excessively store phosphates. PO4 3 minus goes to polyphosphates. This energy is used to store PO4 3 minus in the form of polyphosphates. Typically looks like 0.01 gram of phosphorus per gram of cell for the usual heterotrophs, let us see. But for phosphorus accumulating microorganisms, it can be as high as 0.1 gram of phosphorus per gram of that particular microbe or cell mass, let us say. So, you see it is almost 10 times higher, the phosphorus is going to be stored here. This is what happens in the aerobic phase. So, let us see what is going to happen in the anaerobic phase, right. Anaerobic phase, they are under stress, they do not have energy or such, let us say, right, or they need energy. So, let us see what is going to happen out here. So, you have these polyphosphates that were stored, right. So, during the anaerobic phase, firstly these polyphosphates, not firstly, one of the processes that these polyphosphates, in this process polyphosphates are transformed such that phosphorus or orthophosphates are given out, and obviously energy is given out, energy. Okay. And here again there is no oxygen though, but the carbon source that was present here, let us say, you can think of this, and that is used to form these polyhydroxybutyrates, let us say. So, here you need to have two conditions. What is it? One is anaerobic, because first you want to have this formation of polyhydroxybutyrates, right. You want to have this. So, you will have anaerobic conditions first, and then in the aerobic conditions, what is going to happen? You are going to have these polyhydroxybutyrates being degraded for either production of new cells or such, and then in the same process you are going to have uptake of the phosphorus. But one might ask that, okay, here the phosphorus is being released, phosphorus is being taken up. So, on one hand I am taking it up and in the other hand I am giving it out. So, what is the big deal? It is the same, but well, if I look at the net, more phosphorus is taken in than phosphorus that is released, let us say. So, let us look at one of the aspects or one other aspects. So, some other mechanisms also say that there is a middle path or glycogen that is stored. Glycogen will be stored in the aerobic conditions, such that it can be used during the anaerobic conditions, so that energy is also given out. Again, that is an intermediary, so we do not need to go into that right now. So, here let us say polyphosphates, we talked about adenosine triphosphate energy carriers. So, these are the reactions that can happen, ADP plus PO4 3 minus plus energy, right. So, this is what happens in the anaerobic phase, and in the aerobic phase the opposite happens. Obviously, in the aerobic phase you see that PO4 3 minus and energy from this particular reaction, and ADP goes to ATP. So, these act as the energy carriers in the cell. That is something that I wanted to talk about or mention. Again, no need to complicate things. So, you have what do we say, alternating anaerobic and aerobic conditions. In anaerobic conditions, you are going to have release of phosphorus and or orthophosphates. In aerobic conditions, these what do we say, microbes which have which are thriving here, they will what do we say, accumulate phosphorus. Why? Because they want to be able to use it what do we say, for their energy needs and such, or part of their energy needs later, yes, when they are in anaerobic conditions. So, that is why you need to put them in alternating conditions of anaerobic and aerobic. So, they are going to accumulate what do we say during the aerobic phase and use part of it during the anaerobic phase. That is one aspect to consider. And also here you need to have anaerobic conditions. Why? If there is oxygen, the carbon sources or the kind of microbes that are going to be thrive are going to be different, and you are not going to have phosphorus accumulating organisms. Other than that, you need to have anaerobic conditions because you want to have facultative microbes. These are microbes that can thrive in both anaerobic and aerobic conditions. And why do we need them? Because they can lead to or cause fermentation of the organic compounds and lead to what do we say, formation of what do we say, if I am not wrong, acetic acid or acetate, pardon me, formation of acetate. When we say fermentation product, we say acetate. So, why do we want to prefer formation of acetate? Because these phosphorus accumulating organisms like to use acetate as their what do we say, soluble COD. Okay, so this is another picture. So, we have the relevant references given out here. Let us look at this for a second, right. Again, what do we have? We have facultative bacteria, and this is the anaerobic condition. In the anaerobic condition, again these facultative bacteria via fermentation, right, will lead to formation of acetate, and this acetate is something that these phosphorus removing bacteria or phosphorus accumulating organisms like. So, during this anaerobic phase, again we saw what is going to happen, but here the representation is in a different form. Please note that though, right. They are again talking about carbon storage and such, but you more or less we do agree that phosphorus is being released. So, these aspects you can look at it based on what I just discussed here, let us say, right. So, that is what you have out here. So, we have phosphorus being released, and out here during the aerobic phase, what is going to happen now? This what is it now? You have oxygen present, and again new cells being produced, and what do we say, the carbon source or the PHB going to CO2 and H2, let us say again. But here the key aspect is phosphorus is being taken up in the aerobic phase and phosphorus is being given out in the anaerobic phase, right. So, I believe I looked at this or mentioned this already. So, let us move on. So, luxury uptake, I guess, right, luxury uptake, as in we mentioned stress and no stress conditions, they are in luxury conditions and they take up phosphorus, which will be used during stress conditions. Let us move on. So, phosphorus removal. So, this is a good graph, and I believe I am out of time. So, we will look at this later or in the next session. But again, one aspect is anaerobic conditions, they release phosphorus, and during aerobic conditions they are no more under stress, but would like to take up phosphorus so that it can be used for its what do we say, energy needs, if I may say so, later, right, under the anaerobic conditions, let us say. So, thus we are having net accumulation of phosphorus. So, again anaerobic and aerobic process. So, you have to have a recycle, but we will look at the relevant configurations and such in the next session. And thanking you for your patience, I will end today's session.